Hello, folks. I'm going to talk a little bit about stateful applications and patterns for building stateful applications with serverless. I'm Tanmai. I'm one of the founders at Hasura. Um, a lot of this talk is inspired by the work that we've done with Hasura, with our users, and with Hasura, the product itself. To give you a quick background, Hasura is a GraphQL engine. It's a service that provides an instant GraphQL API on your databases, specifically the Postgres family and other databases coming soon as well. You can also use Hasura to kind of create a unified GraphQL API over multiple data sources, so not just a database, but also GraphQL services and REST services or like SaaS services. Hasura also provides an eventing engine that can help you react to changes on data or react to API events or even time-based events. Hasura runs as a Docker container on your own infrastructure, or also we also have a managed service that we launched recently at hasura.io/cloud. Hasura is open source under the Apache license, and so do check it out on GitHub and let us know what you think. And with that, I shall dive into the talk. So, um, let's talk a little bit about serverless and why developers love it, right? And I'm sure I'm kind of preaching to the choir here, but for me, in my personal journey, when I started looking at serverless functions, I used to hate serverless, and I was like, what are these serverless functions, right? Like this is terrible because I don't get to use whatever framework or language or runtime that I want to use. I have these cold start use cases, especially for API style use cases, and then I can't manipulate state. I don't have shared memory, and so all of these like application server things that I knew are kind of out of the window, right? And so I didn't like it. But over time, I realized that the benefits are actually quite real, and the idea that kind of serverless and specifically serverless functions are moving towards, and the vision that it's moving towards is to say, you know, how do you get to that ultimate place where you can build stuff, deploy it, and just forget about it and let it just run and scale and never have any operational issues ever, right? That's kind of the ultimate vision, right? That's where we want to get to. There is an ergonomic benefit, right, which is basically the experience of building things and the experience of deploying things is tremendously improved. And then there's also an economic benefit, which is kind of twofolds, right? Sometimes you might have particular loads where the cost of running serverless or running things as serverless functions is genuinely lower than the cost of kind of maintaining a service, or even otherwise, there is usually a fairly good impact to your TCO, right? So the total cost of ownership of basically shipping code is reduced because there is a significant amount of expertise that is reduced, and in terms of the number of people that you need and the tooling that you need is goes through a reduction. And these kinds of things that I used to not like about serverless functions, right? These kind of problems are getting solved, right? So if you think about, for example, not being able to use my favorite framework, well, of course, one, the kind of support for different runtimes and different frameworks is itself improving. All of the different serverless vendors and providers and substrates are kind of improving support for runtimes. Specifically with the rise of WebAssembly as a target, because Node.js runtimes have the V8 runtimes and isolates and stuff have gotten really good, and that can you can use that as a WASM target, and then you can have a bunch of languages that you can compile down to WASM and run it, which is nice. There's still caveats there; it's not fully there, but there's kind of progress in that direction. And then of course you have things like Cloud Run, where you can kind of have this Docker container, and so you have a Docker image that just runs everything that you want to run, and a container that's triggered on demand, right? So it's a really nice kind of place in the middle, and things like this are also happening. Um, on the cold starts front, there's obviously been kind of improvements to improve cold starts, and that's kind of what all the vendors are doing. But it's also important to understand that cold starts only really affect synchronous API style use cases, largely. I mean, not I shouldn't say only, but largely affect API style use cases. And the nice thing is that there are patterns that are kind of emerging to solve that problem as well, right? So, for example, one of the things is that if you move to an event-driven style where you're not synchronous, but where processing or that business logic inside the API is running asynchronously, it kind of forces your entire application to become reactive, right? So you kind of make the API call, don't wait for the response, let it run, let it do a bunch of things, come back to you, and then an event gets pushed to you, or you subscribe to an event, and then the client is also reactive, right? And that's not ideal, but that's kind of one of the ways to work around that kind of synchronous problem. But also otherwise, there's kind of genuinely amazing technical stuff that's happening. For example, Cloudflare workers recently launched an update where to kind of avoid even hitting that cold start one, they already had millisecond start times because of the way that they were using isolates instead of kind of trying to bring up full VMs or containers. Um, and now the kind of update that they've launched allows them to run these isolates or boot them while the TLS handshake is happening, because the TLS handshake itself takes a millisecond or two, and especially if you factor in kind of that latency for the client to connect to the edge, and then do the TLS handshake. During that time, you can start the process for firing up the serverless function runtime, right? So there's kind of improvements on that front as well. And then, of course, there's this other problem of dealing with state, which is, well, I'm going to talk about it. So, those hard problems are getting solved as well. I'm I'm joking. I'm going to talk about a bunch of these problems. I'm not going to address all of the possible problems, but just maybe a category or a set of problems. So there's patterns emerging to solve that problem as well. So let's kind of talk a little bit about state, right? So the first question is, is state and being stateful really that important, right? And the answer is yes, because if you're not dealing with state or you don't have any side effects and you're just running compute, well, all you're doing is heating up the CPU or someone's CPU, and in fact, you're heating up the Earth. And given how surprisingly problematic it has been to agree on the fact that the Earth is heating up, don't contribute to it. But kind of more tangibly, right? Like side effects and state is kind of how ultimately humans deal with is what humans deal with, right? And how humans tend to talk to computers and computers talk to computers, by which I mean, the way programs exchange information or the way end users exchange information with programs is through state, right? And so obviously dealing with state is important. But serverless, the entire benefit of serverless is because it's stateless, which means that when you don't deal with things that require shared memory, or you don't deal with things that require you to deal with stateful things, then as a developer, then the cloud vendors and the serverless vendors or the runtimes can absorb guarantees around scaling or around concurrent execution, right? And the reason why they're able to absorb those guarantees is because there's kind of this thing of saying that the developer is not allowed to be stateful, and so the developer can't screw things up, and so, well, your code is stateless. I mean, your code is stateless and your code is scalable. um, but um, but the solution that's kind of emerged to deal with this, to kind of not have state in your code, to not save to a file, to not directly speak to a database, to not have shared memory or deals with things that require shared memory, is to servicify all of these stateful things. So and that's kind of been a general trend that's happening in the world as well, right? More and more things, more and more parts of our stack of portions of code that we used to typically write are becoming services. They're becoming either SaaS services or they're becoming managed services by infrastructure providers, right? And as this kind of servicification is happening, a lot of these services or managed services are absorbing this state, right? So you don't have to deal with it. And to interact with these things, you have to do I/O. So that means you have to kind of, well, you have to contact a remote service to make it do your work. And the idea there is to not make the I/O stateful. So if the I/O is stateless, for example, you're using HTTP, which is kind of designed to be stateless as an interface for the developer, right? I mean, underneath it might be stateful and use a connection pool and stuff like that. But as a developer, your experience, the way you work with I/O is, if you use HTTP, that I/O is stateless as well, right? As opposed to, say, a long-living TCP connection, you're kind of dealing with HTTP where you think in stateless terms, and if there are optimizations to be done, they kind of happen a layer below you. You don't think about it. So that's kind of the broad pattern and the broad trend that we're moving towards. So in that with that kind of context, right, I'm going to talk about three kinds of state. So the first thing I'm going to talk about is, the three kinds of the three different ways of handling state, or three different kinds of state that we have to deal with, right? And while this might not be mutually exclusive, collectively exhaustive, this is kind of a rough list, or almost a set of three heuristics for thinking about the way you have to deal with state. So the first is accessing data, when you need to kind of read data from sources, right? The second is persisting data, when you need to write data to places, so that once your business logic finishes running, you've made some side effect in the world and some state has changed somewhere. And the third is shared memory, which is state that is persisted across, say, consecutive runs. Let's say, for example, you run once, you increment a counter, and then the next time it runs, you increment the same counter, but this counter is only required in memory, right? Let's say, for example, you're doing rate limiting or some kind of memoization or caching to improve performance. You don't want to recompute things, or you don't want to refetch things and rewrite things, right? And you want to deal with it in memory because it's not important to persist, but it's important across consecutive runs. Another thing here is, for example, state that is shared across concurrent runs. And a very typical example there is connection pooling, where you have many different executions that are happening that are then finally kind of speaking to the same system. They might need to, say, share a connection pool to a database, right? And so typically what happens is that if you have like 100 different, say, API calls, they're speaking to a database, you don't need 100 connections to the database. You can have a connection pool of 10, and then you can kind of multiplex these 100 concurrent executions, and you can kind of pick up a connection from the connection pool, and well, it's not truly concurrent in that sense. It's kind of fake concurrency, but you keep that request waiting till you're able to get a connection from the connection pool. But this connection pool, this resource, is maintained in shared memory, right? So that's another example of needing shared memory. Another example of dealing with shared memory, for example, might be things where you sleep and you need to run after a period of time, right? Let's say, for example, I want to sleep for a few seconds or a few minutes, or I want to run at a particular period of time in the future. Very often in an application server, you're able to kind of set that delay, right? And because the application server is running 24/7, you can use the application server to use an internal clock to fire an event so that you can run a piece of code inside the application server. So that's kind of another case of dealing with state inside the context of an application server. You're not persisting stuff, or you're not accessing stuff from a persistent store, but it is kind of in memory and using kind of let's say, a clock. So those are kind of the three types of dealing with state that I'm going to talk about. All right, so let's talk about the first problem here, which is accessing data. So what are kind of the problems when we need to access data, right? And accessing data is kind of like getting inputs that are required for your computation, right? And that's kind of what you need to do when you're accessing data, right? You're fetching the input that is kind of required for your computation. And one thing, when I kind of think about this problem, I like to think about serverless functions as if they're actually web or mobile apps, right? Because if you think about web or mobile apps, their characteristics are very similar to serverless functions. They don't have any shared memory, which means that, by which I mean that, like, two different runs of the mobile app or the web app that run across user 1 and user 2, they don't really have any shared memory. So when you're writing kind of code, you're writing code inside a context. It's not a perfect analogy, but it just helps think about the properties and the kinds of constraints that you would have from other services that we would use. Serverless functions can also support kind of fairly massively concurrent execution, which is that you can have 1,000 serverless functions or 5,000 serverless functions running at the same time, or even hundreds of thousands of serverless functions running at the same time, right? And that's very similar to web and mobile apps, right? You might have 100,000 users that are currently accessing your web app or your API, right? So there's kind of you can have a large amount of concurrent usage. And then, of course, the other interesting thing also is that there is a security context, right? Which means that often when you're running web and mobile apps, there's kind of a boundary, usually kind of a network boundary, that determines a trusted context, right? So they're running outside a trusted context. And very often when we're dealing with serverless functions that are kind of trying to work with data, they might also be running in a security context that is not the same as security context of where your data systems are, right? It might be, say, for example, running on the edge, right? It might be running on a cloud vendor, whereas your data might be in a legacy system. And and uh, and when you have kind of properties like this, you realize that reading data from existing databases where you already have data is hard, right? It's uh, you know it's great to think of serverless as helping us when we're building net new applications, but most of the applications that we build and most of the value that we want to add is on systems that have existing data. And specifically, when you want to read data from these existing systems, you run into kind of these similar challenges that you would run into while building web and mobile apps as well, right? One problem there is that you have a problem of connection management, right? Traditionally, databases and even most modern databases support kind of a limited number of simultaneous connections that you can hold with the database, right? And so you need to do things like connection pooling. You also sometimes have state with the way you're talking to the database, right? For example, if you have read replicas or you're dealing with failovers, then there's a certain amount of state that you have to maintain to understand whether something is a read replica or something is something is a primary, something is a read. And you have maybe failovers where you need to kind of abstract the failover logic. Let's say, for example, you have a geo-distributed database or some kind of sharding logic in place, right? Then you need to kind of understand which shard to connect to as well, right? So the complexity kind of increases even for modern database systems because there's some amount of state associated with connection management, right? And the second is that, well, the second reason why connecting to existing databases is hard is because you need to have security credentials to access that scope data, right? And this is not necessarily unique to serverless functions, but especially because serverless functions can be running wherever, you need to have some kind of security protocol to make sure that you understand what piece of data they're going to have access to. These serverless functions are going to have access to. And so one of the kind of solutions that emerges to this is to say, instead of connecting to a database, let serverless functions kind of connect to a data API or a data service. And a data service should kind of abstract these concerns, these problems, and provide an API, a stateless HTTP API to kind of read or query that data, right? And so here that API can abstract connection management, right? Because it's an HTTP API, it's stateless. That means it's a stateless API, so you don't need to maintain a connection. And again, because it's an API boundary, you can handle some kind of credential exchange. You can implement some kind of authentication and authorization to make sure that you're able to scope in that data, right? And then there's kind of becomes a pattern of how to manage rotation of credentials and whatnot as well. And again, it's not like it's rocket science. It's just that there are patterns that we can leverage and ideas that we can leverage to solve these problems instead of reinventing the wheel. One of the nice things here that we've discovered is that GraphQL is a phenomenal fit because it's a fairly flexible API that allows you to query whatever you want, but at the same time it's restricted. It's not as flexible as a full-on database query API. It's kind of more restricted, so you can scope in access to particular entities or particular objects inside your data source. GraphQL is also great because it's JSON first. That means you don't really need to do any heavy lifting to inside your serverless function to figure out how to get data from the database and convert it to something you want. Marshal, unmarshal that. It's just JSON. And GraphQL is a JSON API, so you're getting results in JSON, which is again great for developers who kind of just want to get work done, deal with JSON because they're probably going to be dealing with JSON on the other end anyway, right? And so it's a good fit for a lot of use cases. Again, a lot of stuff that I'm saying is not applicable 100% of the times, and so you might have data that is not JSON, in which case this doesn't really work. But the other kind of pattern here for accessing data is to not really access data after the serverless function runs, but is to kind of send data to the serverless function and to trigger that serverless function with an event payload. So for example, you kind of react to changes inside a stateful system. So you capture relevant data in the change, and then you deliver that as a payload, which then becomes an input to the serverless function, right? And that's kind of a nice method to deal with it as well, as long as you don't require more data, right? So the data capture mechanism and how you construct the event payload becomes a little bit important, but you can kind of absorb some of that complexity there and then just deliver the event, right? So now your serverless function, the read part of it, at least becomes stateless to a certain degree. So that becomes a way to kind of think about that data access, which is not data access but data given, right? And so those two kind of patterns emerge. Next, let's shift gears to kind of talking about persisting data. And so the problems with persisting data are very similar to the problems of reading data, same kind of database problems. But there's kind of one special problem that is a thorn in my side from experience, which is kind of dealing with transactions, right? I like dealing with. I like transactions because some things are transactional, especially for online applications. And there are two kind of important properties to transactions as a developer, right? One is that transactions absorb an all or nothing kind of semantic, right? So we'll run this transaction. If it fails, things automatically roll back. And the other thing is that you can have concurrent transactions that are operating on the same persisted data, but they can run concurrently, and things will be sane at the end of those updates, right? So if they're operating on the same data, some transactions will fail. If they're operating on data that is independent, it'll be fine. You can have different kinds of transaction semantics, and it's great. It's a massive amount of convenience for developers, right, to not have to think about that. And this basically gets screwed when you move to a place where you can't connect directly to a database to get a transaction API, because a transaction API is usually over a TCP connection, a long-living connection, where you can invoke and run a transaction. So, what are some kinds of solutions that we've seen? Once again, if you kind of think about the data API pattern, in the data API pattern, obviously you get the same benefits of the read side, but specifically talking about transactions, there are two kinds of patterns that we've seen. One is that instead of dealing with the transaction inside the serverless function, you kind of ask the people who are maintaining the data API, the data service, to absorb the transaction logic, expose that as an API endpoint, kind of like a stored procedure, right? Whether it's a stored procedure or whether it's in code doesn't matter, but it kind of feels like a stored procedure, and only the variables are exposed as API parameters, right? So you have to kind of shift that transaction logic, and you have to absorb that into, you have to think of it as stored procedures that the data service gives you, right? So think of it like this. There's databases which have kind of models that you can read, write on, and databases have stored procs. And now in a data service, we'll have APIs that give us the ability to read and write pieces of data, but the data API will also expose a stored proc, right, as an API endpoint. And that kind of becomes a pattern, which hurts agility sometimes, right? Because sometimes for these transactions, you would rather kind of want to run the transaction logic yourself in the business logic that you're writing as a developer. And so there's a little kind of a con here that you have to have, like, there has to be a change management with the person who's building the data API, the team that's building the data API. The other kind of pattern is that transactions over WebSockets, which is not necessarily a great solution. Like, for example, you might not be able to handle massive concurrent loads, but it's kind of similar to the same problem that you would have had of executing transactions anyway, right? If you had a large number of concurrent users all trying to run transactions on the same pieces of data. And so it's kind of the same problem, but if you think about exposing transactions over WebSockets, the nice thing here is that you again have an API boundary. WebSockets are first-class citizens of HTTP. And so again, with kind of this data API model, you can expose WebSockets or transaction semantics over WebSockets, and then you have an API boundary to provide some kind of control around the number of concurrent transactions, the quality of service, who gets to be able to run transactions, who doesn't, and also kind of arbitrating security context, right? So it's not as terrible as running a transaction directly on a database, and there's definitely an element of control there. The con here is that you have to set it up. You have to set up transactions over WebSockets, and then you have to create some kind of a protocol over embedding transaction semantics over a WebSocket protocol, right? So some way of specifying the beginning of a transaction or the end of a transaction. The other kind of approach, if one was the data API approach and the other is the event approach. So if you take the event approach to this, we can break a transaction up into a set of events, right? And so the way we think about it is that we have a series of serverless functions that will run. Each serverless function will make atomic changes to data and then stop. And then at the end of it, maybe they'll just persist data, and that persistence will emit a change event that will go trigger something else, or the serverless function itself can emit a business event and then shut, and then shut itself down. And the challenge here is, and then of course, sorry, the next kind of event that is emitted runs and triggers the next piece of compute. The challenge here is, I mean, this is not really a solution. It's a pain, right? Because you're kind of losing transaction semantics, right? You have to kind of emulate transactions. You're not necessarily, for example, getting that all or nothing style semantics, right? You're not necessarily getting the same kind of concurrent mental model for concurrent execution that you were getting with transactions. And to a degree, you can have things like exactly once processing or in order delivery, which can improve the ergonomics of use, but it does reduce your in practice, that would kind of reduce the performance that you would get in the number of transactions that you can process, because the database is kind of geared towards processing a large number of transactions at the same time. If you start making things, if you start forcing things to be in order delivery, what do you order by? And so you have to understand what the unique objects that you're operating on are, and so you have to make sure that the ordering is done not necessarily just according to time, but the ordering is done according to the data that you're operating on, right? And so it's not a solution, but it's not 100% solution, but it might kind of be able to give you the same properties of a transaction, if you're able to absorb exactly one's delivery of events, or in order delivery, exactly one's processing or in order delivery of events. Let's kind of talk a little bit about shared memory. In the shared memory context, especially for a person like me that comes from a web application server background, serving application requests in production is actually a fairly stateful affair, right? We think that, oh, it's a stateless API that just runs. In practice, it's not, right? And for some of the examples that we talked about, like rate limiting or memoization or caching, right? And the fact that like a function comes up and then dies, it sucks, because you don't have any place to persist this data in memory, right? You can't memoize stuff. You can't increment a counter. You can't decrement a counter and then keep that around, right? You can't maintain an in-application server timer, right? And of course, we talked about why you can't, for example, share a connection pool, which are things that you can do. And so the kind of pattern that emerges here is to say, before I get to that, sorry, WebSockets are another example of having to share in-memory resources across concurrent executions, right? For example, you might have multiple WebSockets that are opened up by clients, and then you might have the same event that needs to be sent to multiple WebSockets, right? To send to multiple clients that are connected. So you kind of need to take that one event and push it down multiple sockets that are connected. And this is very easy. This is much easier to do in an application server kind of environment, right, where you can exploit threads and have multiple threads and stuff like that. But it's much harder to think about that in a serverless environment. And so the kind of solution that's emerging to this is to kind of absorb all of these stateful shared memory portions of an API server into kind of a thicker gateway, right? And so you never invoke a serverless function with an API call directly, but you kind of always go through a gateway to solve some of these problems. And the gateway, because it's now a little bit thicker, because it's absorbing some more work than just a proxy or a load balancing kind of gateway, the gateway has to be fairly flexible and should be declaratively configurable, right? Because you want to deal with it as infrastructure. The entire idea of moving to serverless is that everything else is infrastructure and managed, right? So you don't want to build this gateway and then have a gateway that you're writing code for and managing, unless a platform team is building it out, right? You as a developer don't want to build a gateway and a serverless function, because if you're doing both of these pieces, you might as well just not use serverless functions. And here, for example, if you think about caching, you can like application level caching, right? The application level caching has to be done at the gateway level, not inside your serverless functions, because it's harder to kind of think about caching at the serverless function level. I mean, technically you can kind of use Redis and stuff like that, but let's say there's kind of more of like the in-memory caching that you need to do. And in those cases, what you need to do is set up some kind of hints or a contract between the serverless function and the gateway to exchange information on what is cacheable and how long you can cache it for. And again, I can't go into too much detail because we don't have time for this, but there's some kind of contract that you need to have. Maybe it's a cache control header, maybe it's some HTTP request and response headers that kind of indicate to a gateway, hey, you know what, this resource is cacheable, so the next time we need to operate on this, we can just the gateway itself can just use the cache and not even hit the serverless function. And similarly, when you think about WebSockets, the idea would be to terminate WebSockets at the gateway and then just convert everything into events, right? So you don't have WebSockets after that. The gateway terminates the WebSockets, holds the WebSocket connection, then converts it to an event, delivers the event to a serverless function. The serverless function itself does something, and then that response event or the end result event is then sent back to the WebSocket client. And here, a typical kind of a pattern is to thread that series of events via something like an action ID or via some ID that you can use as a thread, so that if ultimately there is a data change event and the data change event has an action ID, or there's an event queue that has an action ID, your gateway can thread that back and say, oh, you know what, this was for that WebSocket client, right? Or this was for that particular action or message that happened at the WebSocket for this particular WebSocket connection. And again, I can't go into much detail, but this is just kind of an abstract idea of things that the gateway needs to absorb, right? And again, here GraphQL subscriptions turn out to be a really nice fit, because GraphQL subscriptions can be kind of handled at the gateway level, and especially for kind of a web server like web application kind of model, and then the business logic itself can just be run inside serverless functions, right? So the GraphQL subscription part of it, the authorization, the connection management, the concurrent programming stuff can be done at the gateway, and then you can not care about it and just deal with business logic and serverless functions. So at a high level, the way I think about this is that if you come from an application server background, it's kind of like turning the app server inside out, right? A traditional app server has business logic and other things, right? Other things. I'm just going to call it other things. And so what we're doing here is that we're converting the other things into a service and then integrating our business logic over serverless functions. And when we think about integrating business logic with the bits of the app server that we don't want to deal with, there are two ways to deal with it, right? One is that kind of event-based way of dealing with it, which is that we are triggering our business logic on changes, on data changes, on API calls, on time, on WebSocket events, right? And we're pushing events again back, and then the other bits, right, of the app server, kind of like, for example, the gateway or whatever, can pick up from that, right? So there's the events can be one contract, and the other contract is the data API, which is that you need to have another service, or maybe the same service, that also provides an abstraction for giving you a way to read and write data, so that abstracting some of those kind of stateful problems there, so that again your business logic can just be a function that runs, right? So it kind of turns the app server inside out and then just kind of distributes it, right? That's kind of what's happening. It's kind of becoming from one piece into this broken piece. Apologies for my very technical sound that I made, but it kind of breaks up into this piece where you have services that do this other bit of the traditional app server, and then the business logic pieces of the app server, your controllers or functions, they just become serverless functions, right? And of course, there is a impact to this, right? It's not roses, it's not great, but if everything else becomes a service, and then you just have to deal with business logic as serverless functions, that's taking us towards our ideal of that ergonomic and economic benefit of not having to deal with the operations of our business logic, right? The key changes in that have happened that we need to do is, one, there's a phenomenal amount of plumbing that we need to set up to make this work. It's not trivial. And your mental model is shifting a little bit, right? You can't do traditional stuff anymore. Things have shifted a little bit. For example, transactional workloads have to shift to event-driven models. Not a trivial shift to make inside your mind, right? One of the ways that I like to think about this is that we are changing our way of thinking from a CRUD style to a CQRS style, right? And this is kind of one of the things that we've seen with Hasura, and that we've been able to do really well, right? So if you think about, for example, you're using kind of a monolith, and the monolith kind of absorbs all kinds of business logic and then talks to various services, right? Databases and data services. You're kind of moving to a CQRS style, where you're saying we have this kind of thick data gateway, an event gateway, that basically helps us, that gives us kind of a unified API on these data sources. And then this kind of becomes a query engine that can then be used by other serverless functions. And then when you kind of want to invoke functions, what we do inside Hasura with the event engine is that we capture changes on the data sources here and convert them into events, right? We capture time-based events, convert them into events. We capture API calls and WebSockets and convert them into events. And then those events kind of go and ultimately fire serverless business logic. That business logic itself now can speak to other data sources or services or managed services, or even use Hasura as the data API to talk and read write to these data sources, right? And so the idea is that query engine and the event engine helps you kind of abstract away the stateful bits of the app server, and you get to deal only with the stateless bits of the app server. And this is kind of very similar to the CQRS pattern, but again spread out into multiple decoupled components. Again, decoupling is not necessarily great. There's tremendous amounts of pros and cons to it, so you have to think through it carefully, and you don't have to wholesale shift the whole thing, right? The nice thing is you can shift over only parts of your workloads, right? You can only say, well, I'm going to keep most of it in my traditional legacy app and let it be the way it is. But for the new stuff, I'll kind of start moving to this kind of approach, right? And that becomes a possible way of doing migrations. I'm probably a little bit over time, sort of over time. Do feel free to reach out to me on Twitter. I'm Tanmai Go on Twitter, and would love to get into more detail about serverless, state, GraphQL, how things are evolving for developers, what are pain points and what are not pain points. And of course, please do check out Hasura.io as well to see if that helps solve some of your problems with serverless and state. And thank you so much, and hope you have a great day at the rest of the conference.